The electron configurations are going to look somewhat like this, where you have 1s2, 2s2, 2p2, but the 1s, 2s, the big number is going to be the main energy level, the principal quantum number. The superscripts are the number of electrons that are in that sublevel. The 1s2, that's saying that in the 1s sublevel, there are 2 electrons. Which, how many electrons can the s sublevel hold? 2. So is it full? It is full. How many electrons can the p sublevel hold? 6. And so when we have this 1s2, 2s2, 2p2, is the p sublevel full? No, it's not full. You can have a maximum of 6. It only has 2 electrons in the p sublevel. So it's not full. So we'll the superscripts? Those are the number of electrons in that sublevel. The main energy level. We'll talk the energy level of that electron. And we will always deal with the ground state configuration. We won't deal with an excited state. So this is just a diagram of how we fill orbitals, because one of our rules is that you have to fill from the lowest energy level to the highest energy level. The lowest energy level is 1s, so we'll fill here. Then the next is 2s, and then 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p. And we'll learn how, you guys will know exactly how to do this. Here. So there's some rules we have to follow. The Aufbau principle is says that electron occupies the lowest energy an orbital possible. This is for ground state. So we always fill from lowest energy to highest energy. And the lowest energy orbital has to be full before you can move to the next energy sublevel. Number 2, no 2 electrons in an atom can have the same set of 4 quantum numbers. So they can't have the same principal quantum number, all 4 of them, principal, angular momentum, magnetic, and spin quantum numbers. Now they could have the same principal quantum number, same angular momentum quantum number, same magnetic quantum number, but the spin number would be different. So they could be in the same energy level, the same sublevel, the same orbital, but their spin has to be opposite. They'd have plus 1/2 or minus 1/2 for their spin. Or maybe they would have the same energy level, same sublevel, different orbitals, and then they could have the same spin direction. But they're in different orbitals. You can't have the same energy level, same sublevel, same orbital, and the same spin. The orbitals, Hund's rule is that orbitals of equal energy are each occupied by 1 electron before another is added. So p sublevel, how many orbitals do we have? We have three orbitals in this sublevel. So what it's saying, each one of these can hold 2 electrons, but 1 electron goes into this orbital, then 1 electron, then 1 electron, and then the second electron comes in for each of them. So you'd fill 1 at a time, so there'd be 1 electron, 1 electron, 1 electron, and then 2 electrons, 2 electrons, 2 electrons. This is just how they are filled. And that's called Hund's rule. So we looked at our electron configuration, what they look like. There is also an orbital notation, how you can represent these electrons. And this is with lines and arrows. So an unoccupied orbital is just represented by a line. And then you write which orbital it is underneath it. Maybe you'd put 1s underneath of that. And if it has 1 electron, you put 1 arrow in it. So each arrow represents an electron. If you have 2 electrons, you'd have an up and down arrow, both up and down. Why do you think we have to have an up and down? But why can't we have up and up? Negative and positive 1/2. They have to have opposite spins. So really up and down arrow are showing the direction of spin that we have. So an example here, helium or hydrogen has just one electron. The lowest energy level is 1s. This 1s is really underneath this line. And we have only one electron, so we just put one electron in. Helium is in the 1s sublevel also, but it has two electrons, so we put an up and a down arrow. The electron configuration notation, we don't use the lines and arrows. We're showing the number of electrons as a superscript. So hydrogen, we have 1s, and there's only one electron in the hydrogen, so it's 1s1, whereas helium has two electrons in the 1s sublevel, so it's 1s2. They mean the same things, they're just different ways of writing the configurations. This is just another way of orbital filling. 1s, 2s, and you fill 2p, 3s, 3p, 4s, 3d, 4p, 5s, and we'll learn a shortcut rather than just memorizing a table like this. We'll use the periodic table as a guide. Here's a problem. The electron configuration of boron is 1s2, 2s2, 2p1. So how many electrons are in an atom of boron? Just looking at that configuration. 5, I heard. How do you know? Yep, you add the superscripts, 2, 2, and 1, so you'd have 5. I need a different color. So what's the atomic number without looking at the periodic table? 5. Because the atomic number is the number of protons, and if we have 5 electrons, how many protons do we have? It's neutral.
5.
So we have 5, so the protons would be 5, atomic number 5. Now we need to write the orbital notation for boron. So orbital notation means we're going to have lines. So we have our first sublevel is 1s. How many orbitals are in the s sublevel? One orbital. So we have 1s, and we just have one line because there's only one orbital. And how many electrons were in the 1s? 2, it tells us. 1s2. So we have an up and a down arrow. 1s2 here. Next is 2s. How many orbitals are in the 2s sublevel? 4. In the s sublevel, how many orbitals are there? 1. It doesn't matter if it's 1s, 2s, 3s. There's just one orbital. So we just have one line, and this is a 2s. And there's 2 electrons again, so we have an up and a down arrow. And the next is 2p. How many orbitals are in the p sublevel? 3, right? So we need to draw 3 lines for p, because there's 3 orbitals. And we label these all 2p. Your book, I think, may put 2px, 2py, and 2pz underneath of it, just showing the different axes that they're on. If we do it this way, that's good enough. And how many electrons are in the 2p sublevel? 1, so we just need one arrow here. You still need to show these empty orbitals, but we have just one arrow because there's one electron.
Only one line. P is 3 lines.
So how many lines would D have? 5, because there's 5 orbitals in D sublevel.
So they all need to be going up.
No, these are down.
No.
This was, we could fill with one more arrow here, one more arrow here, and then you'd fill the second arrow going down.
Oh, okay.
But we don't have enough electrons in boron to do that. Any other questions on it? So this is the electron configuration of carbon. So how many electrons are in carbon? 6, yes. And what's the atomic number then? 6 as well. It's neutral. 6 electrons means there's 6 protons. The orbital notation for carbon. So 1s first. So we have 1s, 1 orbital, 2 electrons. How many orbitals in 2s? And S has 1. So we have 1, 2. And then how about 2p? How many orbitals? So this is 2p. And we have 2 electrons this time. And Hund's rule says we have to fill in 1 electron in each orbital first, and then we fill the second electron. So we'd have up and up here. It can be down and down, up and up. It can't have a down and an up. Usually you fill one direction first and then the second direction. So there's 2 electrons. Okay. Next, we need to write the electron configuration of the element sulfur, which has an atomic number of 16. Now, let's talk about our little shortcut on our periodic table before we do this. We have what are called blocks in the periodic table. I think this should work, yes. Maybe. This is called, these 2 groups right here is a block, and it's called the S block. Because whenever we fill these two groups, we're filling an S orbital. So this is, how many electrons can be in the S sublevel? 2. So look, if we count 1, 2. If we count over, there's 2 also. So we're going to be able to use this as a guide. So number 1, these numbers down the side also are the main energy levels. So this is like 1s, 2s, 3s, 4s, 5s, 6s, and 7s. The P block is over here. From boron down, across, and over to neon, this is the P block. Helium, just for this purpose, gets moved over here into the S block. Because it only has 2 electrons, it fills in the S sublevel, so it gets moved over. So the P block just goes from boron across to neon and down. How many electrons can be in the P sublevel? 6. So if we count across, 1, 2, 3, 4, 5, 6, we'll be able to count boxes across to see how many electrons are in each sublevel. What about, let's see, this is right here the transition metals from scandium across to zinc and down. This is the D block. How many electrons can be in the D block? 10, so let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going to be able to count across to fill up that D block. And then the F block are the lanthanide and actinide series down here. And how many electrons can be in the F block, or F sublevel? 14, so I bet there's 14 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So when we start to fill, we're always going to start at the lowest energy level, which is right up here at 1s. And let's say, okay, we've seen carbon's electron configuration. Let's see how they got that. So we start here and we have 1s, since we're at the first energy level, we're in the S block. So we have 1s, 1, 2, helium's right here. So it would be 1s2. We're done with that row. So the next element, or the next element that we come to is lithium, which is in the 2, the second energy level, 2s, because this is the S block. And we count across 2s, 1, 2, so it's 2s2. Then what comes after beryllium? electron. And this is we're in the second energy level still. So this is 2. Which block is this? P. And we count over to carbon. If we're doing carbon's electron configuration, 1, 2. So it would just be 2p2. And we'd be done. So let's do sulfurs on this problem. Sulfur is down here, element number 16. So where do we need to start? We need to get to 3p. We always start way up here, 1s, 1, 2. So we'd have 1s, 2. And that's gotten us through helium. What comes after helium? And this is at 2s, 1, 2. So we'd have 2s2. What comes after beryllium? And this would be 2p, 1, 2, 3, 4, 5, 6. So 2p6. What comes after neon? Sodium, which is where? 3s, 1, 2. So we have 3s2. And then after magnesium, aluminum, which is 3p, 1, 2, 3, 4. We stop at sulfur. 3p4. So that accounts for all of the electrons in sulfur. That tells us which sublevels they are in.
Why isn't that 1p boron?
Because we're at the second energy level here, too. Second energy level.
Never have 1p.
You can never have a 1p. Think about the only time.
1 is s.
Yep. Because once we get to p, that corresponded to an L value of 1, right? And the only way we can get 0 and 1 for our L values is if n equals 2. We can't, when n equals 1, we only had an option of an S sublevel. So when n equals 2, that's when we can have S and P. That's the first time we can have P. So what's the first D sublevel? S, P, and D, when we have an option of D, is when we get to the third energy level. So actually, when we get to 4, this is 4s, but our first D sublevel has to be 3D, because the first time we can have a D orbital, 3D sublevel, is when n equals 3, S, P, and D. So even though this is going to be 4s, this will start at 3D, and then we'll go back up to 4p. Okay, we'll get to more of those. So the orbital notation for sulfur, we have 1s, and we have one orbital with 2 electrons. 2s, how many electrons? 2. 2p, how many orbitals? 3. And how many electrons? 6. So we're going to fill, here's where we're going to fill 1, 2, 3, and then put 4, 5, and 6. The 3s has how many orbitals? 1. So we have 3s and how many electrons? And then 3p has how many orbitals? 1, 2, 3. And how many electrons? 4. So we'd have 1, 2, 3, 4. Remember, you had to fill 1 electron at a time in an orbital, and then fill the second electron. So there's our orbital notation for sulfur. So the next question is, how many unpaired electrons does the sulfur atom contain? How many? 2. Yep. This answer is 2. We have these 2 unpaired electrons. And so when we get to bonding, These are the 2 electrons that are available to bond. We're going to be able to do some bonding stuff with those 2 electrons. So we kind of talked about this already, but electrons in the second period start filling the s sublevel and then the p sublevel, where because we looked at the periodic table already, we see second period, we're at the second energy level, and the first is s block, and then we get to the p block. At 2s is considered the highest occupied level. They're going to be called the valence electrons. Anything with the highest main energy level, so like when it has a 2 in front of it, that's going to be the highest main energy level. So 2s. 1s is called the inner shell electrons. So beryllium, boron has how many outer shell electrons? Anything with a 2 energy level, so we'd have 2 plus 1 is 3. So we have 3 outer shell electrons, 2 inner shell electrons. Third period, we start at 3s. We already talked about that. And then once we get to the third period, there's going to be times where it asks for the noble gas, or you'll see the noble gas notation. This just makes it so you don't have to write out this humongous long electron configuration. Because if you had to write the configuration for lead, look where lead is. Lead's way down here. Think about if you start up here, how long that's going to be and going to take. So a noble gas notation is you put the noble gas in brackets that comes before the element. So let's look at lead. What is the noble gas that comes before lead? Xenon. So we'd put xenon in brackets, and then we would start from there at 6s and then complete all the way to the lead. So for sodium, they have this electron configuration because sodium, what's the noble gas that comes before sodium? Neon. So we put neon in brackets, and then we start here with 3s1, and then we'd be at sodium. And that's all we'd have to do. Instead of writing out 1s2, 2s2, 2p6, 3s1, you can make it a little shorter. But for homework and stuff, only write the noble gas notation if it asks for the noble gas notation specifically. Fourth energy level, we have 4s right here. And then, like we said, we go to 3d and then 4p. So it goes 4s, 3d, 4p. And the fifth, we go 5s, and then 4d, and then 5p. 5s, 4d, 5p. So let's do one problem. So we're going to write the complete electron configuration and the noble gas configuration for iron. So if we want to do the complete electron configuration, where do we have to start? At 1s. So we're going to go all the way to iron, which is number 26. But we start at 1s, and we have 2 electrons filling it. Then what comes after helium? 2s, 1, 2. And then what comes after 2s? 2p, 1, 2, 3, 4, 5, 6. Then what comes after 2p? 3s, 1, 2. After 3s, 3p, 1, 2, 3, 4, 5, 6. Then what comes after 3p? 4s, and we count 1, 2. And then after 4s, we start at the d sublevel, and it starts at 3d. So we'd have 1, 2, 3, 4, 5, 6, and that's where we get to iron. We have to start at 3D because the first time we can have a D sublevel is when n equals 3. When n equals 3, we can have 0, 1, and 2, SP, and D. So that's the first time we can have a D sublevel, is at the 3rd energy level. So that's our complete electronic configuration. Let's do the noble gas. What's the noble gas that comes before iron? Argon. And then we start from argon. We would go to the 4s2, 3d6, and that's all we'd have to write then.
So if it was RU, then it'd be 540.
What? RU.
Rubidium, so
Where is that one?
44.
So then you would put krypton in parentheses.
I know, but it'd be 40.
Yep, 40. 40, yep. 40. Okay, we will continue on tomorrow. This will probably, let's say this will be due Wednesday. But you can start working on it now.
There's a green Honda, license plate 14.